Good. Okay, so happy to have our own Andres Arana. We'll talk about effective mapping class groups analysis.
Yep.
Thank you.
Thanks, Alex, for the introduction, and thank you all for being here. Yes, I'll start slowly in case Zoom's not running. So yeah, I'm going to be talking about certain aspects of mapping class group dynamics related to what we've been discussing in the seminar. But to motivate it, I want to start by talking about a counting problem for closed geodesics and hyperbolic surfaces. You've probably seen me talk about, but so that we all start on the same page. I want to start there. And what I'm going to say in the beginning might be familiar to a lot of you, but we're going to move on to new stuff as we go on. Yeah, so let me begin by talking a bit about counting closed geodesics. So I want to do that by looking at perhaps the most familiar counting problem for them, which is the prime geodesic theorem. So for that, let me consider a hyperbolic surface. So X is going to be a closed, connected, oriented hyperbolic surface. So just to picture, so say this is your surface, and on this surface we're going to be interested in being able to count the number of closed geodesics it has. In particular, let's begin by counting perhaps the most unrefined counting. I want to count all primitive closed geodesics on this hyperbolic surface. So this is going to be the number of primitive closed geodesics on X of length less than or equal to some bound L. Yeah, so this surface is going to have several closed geodesics, maybe one here that is simple, maybe one over here with one intersection, and so on. And what I want to be able to tell you is that if you give me a number L, I want to be able to tell you roughly how many of those closed geodesics there are. So that's the basic goal, and this is a famous theorem of, I'm not screwing the reference this time, Selberg and from 56, and via different methods from Margulis in the 70s. And the theorem tells you that you're able to say very sort of on the nose how this guy grows like. This guy, you can write it as a leading term, which looks like a logarithmic integral, which I'm going to write in just a second, plus some error term, which grows at a rate that's less than that. So, and here, maybe let me push this up a bit. Let me write it over here, where this is just the logarithmic integral from 2 to x of dp over log t. This guy grows like, if you want, asymptotically like x over log x. What else do I have to tell you? Well, what's kappa? And kappa is some constant that depends on the geometry of the surface. Yeah. So this is a famous prime geodesic theorem. If you are interested in primitive closed geodesics on your surface, where primitive just means that they don't wrap around themselves more than once, then your counting function has a leading term, which is this logarithmic integral, which asymptotically is like e to the L over L, and you have some error term which grows with a gap with respect to the leading term. Yep. And one could be, in the case of this theorem, one has an expansion and it's way more precise, but at least the gap, we can say that it depends on the geometry of the surface. Yep. So that's this result, but we want to do countings where we don't only care about primitive closed geodesics, but we want to put some sort of adjective in front of them and be a bit more precise. So to do that, let me talk about what topological type means. this is going to be sort of a very refined notion of like an adjective we can put, because certainly we could say, oh, maybe we care about all simple closed geodesics that have less than a certain length, or all of them that have less than one intersection, something like that. We want sort of the most refined way to characterize geodesics that we can at this level. So that's what I'm going to define for you. So I'm going to say that two closed curves, gamma 1 and gamma 2 on homeomorphic surfaces, S1 and S2 have the same topological type. If there exists a homeo from one surface to the other, such that the homeo applied to the first curve is free homotopic to the second curve. Yep. So that's sort of formally what it means, but roughly what this definition is telling you is that two curves have the same topological type if, after allowing yourself to wiggle them, they cut the surface in the same pattern. So to give you an example of two curves that have the same topological type. So here you have one curve over here, this curve in green, and maybe you have this other curve in green over here. A priori, they might look different, but you can see that if you cut your surface either using this curve or this curve, in both cases, you're going to get a surface of genus 1 that has two boundary components. So these are two curves that have the same topological type. A curve that has a different topological type, for instance, in this category of simple curves, is this one over here. Yeah. Because that one is cutting your surface into two genus 1 components with genus 1 surfaces with one boundary component. And we can obviously go a bit more. We can draw other topological types. Maybe let me draw a few of them here. I'm not, and I want to make this clear, I'm not restricting myself to simple closed curves in any sense. I will actually want to look at curves that are very non-simple. So for instance, I might want to look at curves that have one intersection, but even more, I want to look at curves that sort of see the whole surface, meaning that they cut the surface into disks. So that's what we usually call a filling curve. And it might be hard to draw one out of your imagination. So I have a little picture here to help me. Yeah, it looks very complicated, but you can certainly come up with many curves that have this property that they cut your surface into disks, even after you sort of tighten them as much as you can. So this is what we call, so maybe to tell you different names, these are topological types of simple closed curves, and these are topological types of filling closed curves. Maybe to make it more clear, what does filling mean? So just to give you a proper definition, filling, this curve is filling because no matter what other closed curve you give me, you can never isotope it away from this curve. You will always intersect the blue curve. Yeah. If you draw any closed loop here on this surface, you will always intersect the blue one, and you cannot wiggle it around or do anything to save yourself from that situation.
In your equivalence, you allow same free homotopic class also. Yep. So why does the topological property remain invariant by such?
I mean, so the property of being simple doesn't remain invariant, as you say, because I can obviously, I don't know, take this guy and free homotope it to do something absurd like that, and it wouldn't be simple. So the property of being simple is not preserved, but you sort of want to look at the class of all curves that are simple. And the way this is going to matter is when you look at geodesics, as we're going to do, they tend to have the simplest structure possible. So as a geodesic is tight, geodesics that are in the class of a simple closed curve will always be simple. And sort of the same thing will happen with all of the other pictures. When you look at geodesics in that class, they'll always be maximally tight, and so they'll assume the simplest structure possible. Yeah, so that's a very good question. Okay, so these are the different types you can witness, but maybe let me say one thing that I think is good for intuition, and that's that, okay, you have these types. I just want to mention that this is a very sparse situation. It's very uncommon for closed geodesics, say, to be simple. If you let them run for long enough, they're going to intersect themselves. And actually, this is a situation that's generic. Yeah, in some precise sense that I won't explain for the sake of time, but you can show that that the generic situation for closed geodesics is that they fill the surface, that you cannot avoid them. So in general, that's what we are going to be aiming for, and those are the geodesics that we'll care most about. Yeah. So any questions? Okay, then maybe let me mention.
So the sparse, yes, you will explain in a more precise way.
Yeah. Yeah, the sparseness will become clear when I state the following. So we want to, what's the counting problem that we care about now? So I was saying that I want to put an adjective that's not just primitive. I want to put something more refined. So let me consider again a hyperbolic surface with the same properties as above. Maybe let me say also that it's going to have a given genus be bigger than or equal to 2, because it's hyperbolic. And on this surface, I want to consider a closed curve. And now, the counting function that I want to look at is sort of what you expect, given what I've been saying. I want to count the number of closed geodesics X of the same topological type as gamma, and I don't know why I wrote 6, gamma and length less than or equal to. Yeah. So instead of asking for them to be primitive, we ask them to have the same topological type as gamma. And there are many theorems in this direction, starting with Mirzahani's thesis, but I want to mention one, which is effective, and it's more of the flavor of what I want to discuss. So let me mention a theorem of Eskin, Mirzahani, and Mohammadi. Eskin, Mirzahani, Mohammadi. This is from 2019, and what the theorem says is that if gamma is simple, that what you can say is that this function, this Cx gamma L, you can describe very well how it grows. It has a leading term of order a polynomial of degree 60 minus 6, and it has an error term depending on the data, but which has a power saving with respect to the leading term. And here, let me just tell you what C and kappa are. C is just a constant, positive constant depending on the data, the surface and the type that you care about. This is just positive. C is that, and kappa is a constant that sort of magically only depends on the genus. Yep. And to go back to Jimbo's question, you can already see here that the simple case is very sparse, because this theorem tells you that if you fix a type of simple closed curve, the counting grows polynomially like L to the 60 minus 6. And it's not hard to show that there are only finitely many types of simple closed curves. So for instance, here I drew you the only 2 types that there are in genus 2, and that's all there are. So you can see that this is growing polynomially while this is growing exponentially. So certainly this is a very sparse case. And you can, just using that idea, you can imagine what being generic means here. Filling
What
accounts.
kind of function is C of X and gamma, do you know?
So this is a function which splits independently in the hyperbolic surface and the curve.
But as a function on moduli.
Yeah, so it splits as a function on a piece that depends on moduli space and a piece that depends on the curve.
Factors.
Yeah, this is a rational number that you can compute. This you cannot compute, but you know properties of the function. I mean, you could compute.
I mean, it's smooth, right?
Yeah, it's smooth. It has some convexity properties. I mean, you could compute it using some interval arithmetics or things like that, but it's a bit more convoluted. Yeah, but you can approximate it in different ways.
And you understand the asymptotic
Of this, yeah. So in as you pinch a curve, this blows up. And moreover, you know that it's L2 with respect to the Bay-Pearson measure. So you kind of have a very precise understanding of the singularities.
If you associate with gamma, you know, the conjugacy class in the fundamental group, then this is an invariant of the conjugacy class, I bet, right? But
yeah, this is an invariant of the mapping class group orbit. So
even of the mapping class orbit.
Yeah.
So I'm a bit confused here because those elements in the fundamental group, which are conjugate to the representative of gamma, are not in this counting.
the elements which are conjugate, I mean,
Like if you
Yeah.
kind of change the base.
yeah, if you change the base point, I mean, if you do something like that, you loop around and then you,
So it's not topologically.
but this is sort of free homotopic too.
Oh, I see. So it's
You're-
counted as one.
Yeah, yeah.
I mean, like the conjugate class is counted as only
Yeah.
one contribution. Okay.
Yeah, so as you're looking at the geodesics or like the geodesic representatives if you want, that's what's happening here. Even if you change the base point, this has the same geodesic representative as your original curve. Like when you tighten this guy up, this extra piece just goes away.
And all the other topological can be obtained from the mapping class group. I wonder if this can be translated to just in the terms of the action on the mapping class group on the conjugacy classes of the fundamental group. Namely, can we say that Cx gamma L is kind of at least Lifshitz equivalent to a function which will count the following. Count, you know, you fix set of generators for the fundamental group, and you ask how many conjugacy classes will appear in the automorphic orbit of gamma. When I say automorphic, I mean under the automorphism group of gamma, which is really the action of the mapping class group on the conjugacy classes. Is the two things are related?
Yeah, I think I'm going to write a formulation of this, which will look kind of what you say. I don't know if it will exactly be that, but maybe let me write it down and then maybe it will become more obvious. Yeah, I'll write that in a couple of words. I'll just write this in a more clear way than that. What did I want to?
Function torus, this is the Markov numbers, which I'll be talking about, these guys. They're all the same thing.
Everything is Markov.
Yeah. So yeah, so I guess I haven't stated the theorem that I wanted to mention, so maybe let me state that. So erase. So here's a theorem of myself. So say this here, and the theorem is that the same type of estimates, the same type estimate holds the generic, and this is what I want to highlight, the generic case when gamma is field. Yep. So the above theorem is exclusive.
So it's still 6G minus 6 in the exponent.
Yeah, so you write exactly the same theorem, but you change simple for filling. Yeah, so it's just change this by this. So the same type of estimate.
This is also sparse.
Hmm?
So this is also sparse.
Being filling is not sparse. I mean, looking at one type is sparse because that always will grow like L to the 6G minus 6. But if you look at all filling at the same time, that's going to grow like the leading term in the first counting result that I mentioned.
I see.
Yeah, so it exhibits the same polynomial behavior.
So if you let the gamma exhaust all the classes, filling classes, so can you get some asymptotic description?
I mean, it's going to be hard to sum this estimate over all, say, gamma, because there are infinitely many types of filling curves, and they depend on, and the error term depends on the type that you look at. So you don't have such good control that you would be able to, and the leading thing also depends on gamma, so you would need to have like a lot of.
But when gamma goes to all the filling classes, do you expect the density is positive?
When gamma what?
Exhaust all the filling classes, do you expect the density to be positive?
The density of counting all filling curves?
Yeah, I mean, you mentioned the Selberg-Margulis.
I mean, it should be, if you do a Selberg-Margulis theorem where you replace primitive by filling, you should be getting exactly the same result.
Okay.
That's sort of what I mean by generic, actually. Like it covers the whole counting. You don't need more than that.
Yeah. Okay.
Yeah, thank you for the question.
And is that something someone could prove if they wanted to?
Yeah. So there are several results. The best way that I could explain it is that the geodesic flow is exponentially mixing. So it's effectively mixing and very quickly mixing. So you just use that result to approximate.
And that's where the kappa comes from, the exponential.
Yeah. It's also where the error comes from. What else here I want to mention? Yeah, I will try to sketch a proof of this by the end of the talk, but for now, let me just mention you an upshot. And it's how do you prove this? Well, I haven't mentioned anything about the proof up there, but the proof certainly uses the simplicity in a very important way. So you want to prove in the case where you are feeling sort of the opposite end, and you have to come up with new ideas. But the main thing that you want to try to do is to communicate with phase with rich dynamics. And the space for us, this is going to be the Teichmüller space, or as Bill was calling it, the Fricke space. So it's one of these character varieties that we care about, and the dynamics is going to be the dynamics of the Teichmüller geodesic flow. I'm going to introduce later in the talk. That's sort of the rough idea of what we want to do, and maybe the framework or the how we want to do it is by introducing sort of a theory of effective mapping class group dynamics. Yep. And what I want to do now is explain you, okay, so I'll explain what the point of view that I want to take on Teichmüller space. I'll tell you a bit about the Teichmüller geodesic flow, and I'll focus mostly on what these set of words mean. What do I mean by having that kind of results? Yeah. Okay, so I say I want to develop some sort of theory of mapping class group dynamics. I should tell you what spaces I care where the mapping class group acts on, and I guess you can guess several of them, but let me tell you the two that I'm most interested in. So just to make the notation easier for me, let me just tell you how I'll denote the mapping class group. So I'll let this G be a close connected, let me not write that down, but it's a close connected oriented surface of genus G. These two. And what else do I want? I want to consider the mapping class group of this surface. So that I'll denote by mod G. And so that's just a group of orientation preserving homeomorphisms up to isolate. The group that we've cared about. And the first sort of space where this acts on, and which I'll care, and this is to go back to Alex's question, is I want to look at the mapping class group acting on the space of free homotopy classes. Closed curves on my surface. Yeah. There's certainly an action. If I give you a free homotopy class, you can apply the mapping class group, any mapping class, and it's gonna give you another free homotopy class. And using this action, maybe just to show you why I care about this action, let me go back to the counting function that we have over here. Remember, this is just closed geodesics on your surface X that have the same topological type as gamma. And we could think about this as the following.
Can I ask a historical question? Because I vaguely remember Mirzakhani's vial or most lectures here some years ago, and she described that theorem with simple. But then she was talking about cases where they like intersect in 2 or 3 points.
Yeah.
So a generalization of the simple, but not your general case. Is that the point?
Of what?
That she done.
Oh yeah. So there's certain simple cases where not simple in that sense, but if you have curves that have one intersection, you can reduce to the simple case.
And that's what she was talking about.
Yeah, I think that would be what she was talking about, because she knew like a trick to do that, and she knew a trick to do certain. If you're in a very simple situation, you can reduce to the simple case by.
But not your case.
Yeah, not my case, but yeah, there's some techniques like smoothing out your singularity, and then you can keep track of the length using trace identity. Okay, so what was I saying? Yeah, this counting function, now I'll write in a slightly different way. I'll just look at curves in the mapping class group orbit of gamma. And I'll ask which of those curves have a geodesic representative that has length less than or equal to L on my hyperbolic surface. Yeah, so this counting function that I originally cared about, which seemed like a counting function of geodesics, is a counting function of a mapping class group orbit in this space of free homotopy classes. This is prescribing the type. Over here, I'm looking at a fixed mapping class group orbit, and this is prescribing the length.
What is this notation? Length of?
This is the length of the geodesic representative of alpha on the surface X.
Ah, I see.
Yep.
And alpha is the representative of gamma.
Yeah, alpha is a curve in the mapping class group orbit of gamma. You take a curve in the mapping class group orbit of gamma, and you look at it with respect to the hyperbolic metric X, say. I'm trying to think about.
So you take all of them, like you take all the representatives of the orbit of gamma.
Yeah, for each guy in the orbit, I look at its geodesic representative, which is unique. And for that one, I check if the length is less than or equal to L or not.
So this is like I mean, this set is like the union over all alpha in the
This is just, I looked at this is maybe, if you want, this is a free homotopy class in the orbit of the free homotopy class of gamma. And in each free homotopy class, there is a unique geodesic representative.
I see.
So that's what I mean.
I see.
Yep. Any other questions? Okay, so this is one place where I want the mapping class group to act, and the other place is our famous frequency space. So maybe let's bring this guy down. Okay, so over here. So
Free homotopy classes are the same thing as conjugacy classes? Free homotopy classes are the same thing as conjugacy classes?
Yeah, for closed geodesics.
You have to assume something.
Yeah.
That's how Silver gets it from his trace formula. Exactly that relation. Conjugate, he's counting conjugacy classes. Primitive conjugacy.
So, yeah, what did I want to say? The other place where we want the mapping class group orbit to act is this case of discrete faithful representations from the fundamental group of the surface to PSL2R, say, modulo conjugation by PSL2R. This is the frequency space as we're calling it. I want to take a more sort of geometric perspective on this space, and for that, let me call it and introduce it as the Teichmüller space. This is going to be Teichmüller space. The Teichmüller space for me is just going to be a space of pairs x, comma, phi, where x is a Riemann surface. And phi is just a homeomorphism from my original surface onto x. Yeah, and this has some equivalence relation, which maybe I'll explain just say isotopy and conformal. Some equivalence relation, but let me tell you what this space is. This is sort of going to be a cover of the moduli space of Riemann surfaces, where you not only remember a Riemann surface, but remember how your surface as G, a surface that you fixed beforehand, is sort of wearing it on top of itself. Yeah, that's what this diffeomorphism, this homeomorphism means. Like you can pull the Riemann surface structure over here to get a Riemann surface structure over here. That's sort of what we're doing. This is useful, for instance, because it lets you communicate all points in this Teichmüller space. So if you give me a simple closed or any closed curve on this surface, that corresponds to a closed curve on X by mapping it through this map. And that's why we usually call this guy a marking, because it's sort of just marking our surface X with respect to our base surface SG. So these two spaces, this and these are equivalent. Maybe let me write like that.
What does DS mean?
Oh, discrete and faithful representations. Discrete, faithful. Yeah, these spaces are equivalent. Maybe let me not say much about that, but it's just an exercise in, if you want, you can use uniformization or just these are surfaces, so they have very easy topological theory. The action of the mapping class group when I write the frequency space as the Teichmüller space is very simple. So it acts on here, and how does it act? Well, phi applied to a marked surface is just the same surface, but with a different mark. Yep. And you can see that, okay, so this is Teichmüller space, this is the action. This action is properly discontinuous. And in particular, you can take the quotient and you recover the famous moduli space of genus G Riemann surfaces. This is just moduli space. Yeah. Just because you have marked surfaces, you have a marking changing action, you quotient out by it, you forget the marking. That's basically what we're saying. And okay, so the action is properly discontinuous, and you might say, okay, that should make it very boring, but what I want to defend during this talk is the fact that studying properly this continuous action is relevant and is very interesting. So hopefully by the end of the talk, I have convinced you of that. But for now, I want our picture in our mind to be that Teichmüller space is some sort of disk. It's topologically a disk, and it has this properly discontinuous action of the mapping class group. So this is when I act by one guy, this is when I act by another guy, etc. And this is going to look very analogous to having a lattice acting on the unit disk. But that's sort of analogy for now. I should, before defending the point that it's interesting to study this section, I should tell you more about the geometry of the space, because else we have sort of nothing to say. So that's what I want to do now. Yeah. And for that, I'm going to use this picture that's been sitting here for a long time. So I want to tell you what the geometry is. So in particular, I'll describe you a flow or a family of deformations on this Teichmüller space. Yep. And what I've drawn here for you, this is a holomorphic quadratic differential. Quadratic differential on a Riemann surface X. So what's a quadratic differential? So I could give an analytic definition or whatever, but I just want to stick to this one. A quadratic differential is just a polygon that you draw on the plane, which has some identifications of its sides by either translation, like these sides in red, or translation and 180-degree rotation, like these sides in blue. Yeah. So this polygon, which apparently seems very innocent, encodes a lot of information. It clearly encodes a topological surface. You just carry out the gluings, you get a surface. But it's also encoding a Riemann surface because all the identifications that are defined are holomorphic. Yeah, translation is a holomorphic map, and multiplication by -1, which is 180-degree rotation, is also holomorphic. So you get a Riemann surface, and it has some singular points which you can plug, and there's no problem with that. But what this picture will encode, and let me write it here, is this is equal to the information of a Riemann surface, the surface that you get by gluing this out, plus a quadratic differential, to be more precise. And what this quadratic differential, what this extra information of having the polygon gives me, is that it prescribes a one parameter family of deformation.
I mean, real or complex parameter?
Real. One real parameter family of deformations, and the deformations correspond to just applying this matrix e to the t, e to the minus t to the polygon. Yep. So let me explain. You start with this polygon. This encodes a Riemann surface with some markings, and you start here. And now you should think about this polygon to give you a direction. And what you're going to do is you're going to apply this matrix to the polygon, and that's going to stretch it in the horizontal direction and shrink it in the vertical direction. Yeah, this is not a holomorphic transformation, so this underlying Riemann surface is clearly changing as I do that. And you can also carry out the marking, and you can see that this will correspond to some sort of geodesic on this space. As you apply this guy more and more, this guy is getting stretched more, shrunk more, and that's giving you different Riemann surfaces as you vary the parameter. Yep. So that's what this is, and these are actually the unit speed geodesics of a metric. We call it Teichmüller metric.
SL to area.
Yeah, there's an action of SL2R, as you're saying.
You're just sticking to the diagonal.
Yeah, I'm sticking to the diagonal, but you have a complete action of SL2R on these polygons, and it's extremely relevant to study the full action of SL2R. But for now, I just want to look at these geodesics. Yep. Okay, so
Can you explain the relation between this pixel and the holomorphic notion of quadratic difference?
and the holomorphic what?
The holomorphic notion of quadratic difference.
Yeah, so the usual notion of quadratic differential is that it should be something which in local coordinates looks something like that. And if I give you a polygon, you can get the differential by lifting the dz squared form on the polygon. And so if I look at the polygon with dz squared, that gives me a quadratic differential. And backwards, if you have this analytic definition up to orientation, this corresponds to you can look at a local square root and you're going to have something that looks like dz, and then you can just integrate this form, and that's going to give you sort of x coordinates and y coordinates that give you local charts that look like translation. Yeah. So yeah, that's the connection between the usual analytic definition and this other picture.
And at the zeros, you have singularity.
Yeah, the zeros of these quadratic differential corresponds to the singularities of the polygons or the vertices, which have a cone angle around them.
If that for the differential, you have integrality of the order of the pole. So that's
Yeah, the same thing happens here. If you add up the angles at these guys, they're always going to add up to a multiple of pi. Yeah, that has to do with the fact that the identifications are by translation or rotation.
this is stable by.
Yeah, all of this is stable by the order of the singularities, and everything is stable by the action of this guy. So that information is preserved throughout. Mhm. Any other questions?
What's that action in terms of the action on the global sections of omega squared, omega 1 squared that you just wrote down? You have this action on holomorphic differentials. What is it analytically?
I mean, it's, you can think about, I don't know, if you have like, if locally, let me think about, you have a square root, you have something like this, dz equals dx plus I dy. This is just like multiplying this guy by e to the t and this guy by e to the minus t. But it's sort of more complicated than that because the holomorphic structure is changing. So it's not, I mean, you can write what it is. You can write a Beltrami differential that represents this deformation, but it's not so, you can write things explicitly, but it's not as useful, I would say, as looking at the polygon. Does that answer your question?
Yes, sure, that's fine. Thank you.
In split geodesics can be written like this?
Yeah, all geodesics, all for this metric, which I haven't defined, can be written like a polygon and you apply this matrix. So this describes a metric which is actually complete. And I've described for you all the geodesics. Thank you. Okay, so that's maybe enough of introducing this geometry. Maybe let me go back to the thing that we actually want to do. We want to do some counting or study the action of the mapping class group. We're good on time to mention the two things that I wanted to mention. So maybe let me erase here. So I want to go back to my
Teichmüller metric in terms of the definition, in terms of quasi-conformal maps and the extreme of dilatation, it's the same, right?
It's
the same type of metric.
Yeah, same type of.
You're never going to look at it that way.
Yeah. I'm just not going that way. Okay, so what do I want to say? Here's a question. I said that we want to study the action of the mapping class group on the Fricke space, and it's properly discontinuous. And someone might come and challenge me, then why it's interesting. So here's a question.
Nobody said that's not interesting.
Here's a question: is how does the mapping class group distribute points over over Teichmüller space. And well, what do I mean? Here you have, maybe let me say reduce space here. What do I mean? So here's Teichmüller space. It looks like a disk. I have a point X here, and I have the mapping class group of another point, which I'm going to draw in yellow. So points are around, and these are like the mapping class group orbit of Y. What I want to do is I want to start growing a ball of radius R around this X. Yeah, some ball of radius R around X. In this metric, in this Teichmüller metric, which I didn't define the metric, but I told you what the unit speed geodesics are. So that's equivalent. Any point here is one that you can access through one of these polygonal pictures, starting from your Riemann surface X. And I want to start growing this ball, and I want to know how many points of this mapping class group orbit land inside this ball. Yeah.
Also the ball is convex.
It's not, but yeah, but we're still going to be able to do it.
But it is growing, you know.
Yeah, it is growing, but it has this lack of convexity, which is actually a very recent result. It wasn't known beforehand. So we're going to make it grow. So maybe let me write it here for 2 points X, Y in Teichmüller space. We're going to be interested in the number of points in the mapping class group orbit of Y that land inside the ball of radius R of X. And you might have seen this before being done on H2. So if you have the hyperbolic space, you have the action of a lattice. This is something very similar to that. Yep. And let me mention our result. So in this direction. So I'm gonna, I just want to mention the work of Atreya, Bufetov, Eskin, and Mirzahani. Atreya, Bufetov, Eskin, and Mirzahani. This is from 2012. And also there's work of myself more recently from 2020, where we prove that quantity that we care about, this guy over here, in the number of points that lie inside the ball of radius R, grows like an exponential of order 6g minus 6 plus some power saving error term. E to the 6g minus 6 minus kappa times R. And here I should say that magically the constant only depends on the genus. That's just magic. Maybe let me not say more than that. And the gap also
Doesn't depend on the base point.
no. Yeah, it's very surprising.
That's something recent. Right?
Yeah, it's from around, it's later than this result.
Yeah, I didn't know that.
Yeah, they didn't know that. It doesn't depend on the base point. Let me say that their result is the asymptotic case. So you prove this without an error term. And what I did was prove the result with an error term. Yeah. So just as happens in the case of H2, you have an exponential growth of the order of the dimension, and you have a power saving error term. And yeah, I won't have much time to comment on the proof, but maybe let me write here a small upshot, just because I want to say a little bit about it. The whole point here is that, okay, you're studying how many points land in the mapping class of order of Y, land inside this ball around X, and it's a ball in the Teichmüller metric. So you have geometry, and what happens is that the relevant geometry, this Teichmüller geometry, is very rich, and in particular, the Teichmüller geodesic flow, the flow that I described up above, has very rich dynamics. So in particular, when you look at it on moduli space, it's exponentially mixing. It has very nice hyperbolicity properties, and usually when you have that, you can carry out proofs of this type.
Ergodic in particular.
Yeah, it's ergodic in particular, and error terms come from exponential mixing. which also has to do with the spectral gap of the
Who proved the exponential mixing?
exponential mixing is by Avila, Gusel, Yokos, and Resende. That's a large group of people. Yeah. Questions about this type of problem? So I'm going to move to something slightly different now. Because I said, okay, so the mapping class will be acting on this frequency space. Here's a relevant question for this properly discontinuous action that we can study. Here's an answer. Now, the other space where it's acting is on the space of closed curves. So I want to tell you what a result looks like there. So maybe let me write it over here. So here's another question very similar to that one, but for a surface. How does the mapping class group distribute points over a surface? So what do I mean? So here you have a genus 2 surface. And let me draw for you a curve in blue. What I want to start doing is moving this blue curve by the action of the mapping class group and seeing where does it land on this surface. So how am I going to keep track of that? Just as a first order approximation, let me draw a curve in orange, and I'll apply mapping classes to this curve, and I'll see how many times they end up intersecting this curve here. Yeah. So say I apply one mapping class, it will always have the same topological type. I apply one mapping class, I might end up here and be very unlucky. I still see 0 intersections, but maybe next time I'm a bit more lucky and I land up here and I maybe end up seeing 2 intersections. Maybe I apply another mapping class and I'm way more lucky and I see a bunch of crossings over here and I end up seeing many intersections. So let's say this is phi 1 of alpha, this is phi 2 of alpha. Alpha, let's call this guy beta.
So you move in, or you always take the geodesic representative.
Yeah. Let's say these are the geodesic representatives if we want. Yeah, so that the notion of isotopy doesn't bother us. So I'll just move it by the mapping class and then I'll tighten it to a geodesic representative. And the question is, how many times are these guys intersecting? And the answer is going to be a bit unexpected. The answer is that we're going to give an answer to this in a very dynamical way. We're going to say that the action of the mapping class group on closed curves effectively tracks the action on Teichmüller space. Yep. So the key word here is track. And what I want to do in the minutes that I have is explain you what tracking means.
This is sort of like in the hyperbolic case that if you're looking at the geodesic ball of large radius, it becomes like a horocycle. Is it related to that? In other words,
it has some sort of flavor like that, but it's not exactly. Yeah, but it has like a, if you squint, you can see something of that sort going on.
So the point of this track is that your main theorem will follow from the tracking.
Yeah, that's the main point. So let me tell you what tracking means. And if I have a few minutes, I'll maybe go back to the original statement, but here's what tracking means. So I usually call this a tracking principle. So maybe let me write that name here.
There's a kind of simple case, right?
Yeah.
There's some coordinates which were like linear coordinates. It was the same way she got the one from here. Is it not?
So Mirzani did kind of more what you mentioned. So in the result, the way that she got was to approximate like horocycles by balls in the Teichmüller. Yeah. So what was I saying? So, oh yeah, tracking. So this is what I call a tracking principle. So what do we have as data? We have these two curves, alpha and beta, are closed curves on our surface. And I want to, because I claim that it's tracking the action of Teichmüller space, let me fix a couple of base points on Teichmüller space. The quantity that we care about is we want to know something about the intersection number between alpha and g dot beta as g moves in the mapping class group orbit. In the mapping class group. Yeah.
And always taking geodesics.
Yeah. So this I means geometric intersection number, which means that you look at the least number of intersections between representatives in the free homotopy class of alpha and g dot beta. And that's equivalent to tightening them to geodesics in some hyperbolic metric and counting the intersections. Yeah. So that's that. And we care about that quantity. And let me write for you what a tracking principle should look like. So here's a theorem of myself. This is from this year. And let me write it exactly as I wrote it here for all, but quantitatively few. Mapping classes. The position of g dot y in Teichmüller space relative to x determines the intersection number that I care about up to a power saving error.
Position, what does that mean?
Yeah, the position, what does that mean? Thanks for the question. What does that thing mean? It means the following. So let me draw it over here. Okay, say goodbye to this guy. So I won't write you. Okay, so this theorem is an explicit formula for this guy in terms of data that relates to the position. The position means something like this. If I know where x is and I know where this g dot y, what I want to know is this distance over here, like say that's r, and I want to know the direction of the Teichmüller geodesics. So I want to know something about the quadratic differential. So
That's like an angle.
yeah, it's sort of like an angle that you're moving. If you know where g dot y is relative to x in terms of distance and direction, you can pretty much nail down what this intersection number is. So in that sense, the action of the mapping class group on curves is tracking the action on Teichmüller space. If I understand the action on Teichmüller space well enough, I'll understand the action on curves.
And quantitatively few means far fewer than e to the 6.
Yeah, exactly.
Swallow the much smaller.
Yeah, so quantitatively few is growing less than this guy with
That's
some
an error. Right?
yeah, like yeah, growing like an error term like this. Yeah, and maybe we're running a bit short on time, so let me mention a couple of things. So okay, so I wanted to do and I'll end it here. So I wanted to do some counting problem where let's remind ourselves we had this guy and this was, as we were saying, we count over the mapping class group orbit of gamma and we look at geodesic representatives that have length less than or equal to L.
What's the relationship between alpha, beta, xy?
Oh, xy are some points that I fix on Teichmüller space. They're arbitrary. They have no relation with alpha and beta, but the orbit of beta under the mapping class group is going to shadow the orbit of y under the mapping class group. That's sort of that's what the theorem tells you. We just fix 2 points, and then you have this sort of shadowing thing happening here.
Oh, okay.
Okay, so we started with this. Let me mention one thing that I haven't mentioned and which is key. So here I told you how to estimate intersection numbers, and in my counting function, there's a length. So what's the point? The point is a very important remark of Bonahon, which is that intersection numbers approximate lengths. Numbers. I would like to say more, but I'm running short time. I'll just say it like this. So intersection numbers will approximate length, and so you will have from information about these intersection numbers, you will get information about this length over here for this hyperbolic metric. This even works for any negatively curved Riemannian metric, so it's even more powerful. But in our case, we can use it for that. So what's the upshot then? That if you use the tracking principle, you will reduce this to a count multi-orbit on Teichmüller space, and then you use counting there. You need a more refined version than the one that I described. You need what's called a bisector count, but let me just say using that counting, you just are able to solve this problem with a nice power saving error term. Yeah, that's sort of what I want to say. And to finish it, hopefully I've convinced you that studying properly discontinuous actions is relevant. So yeah, I'll just finish it there.
Why are you defensive about that? Some of us do it for a living for many, many years.
Oh no, when I talk with Bill, he usually is describing like, oh, in this character variety, the action is proper. So it's not interesting. That was just that point.
Okay, we don't have time, but still, if somebody wants a quick question. If not, there were many questions during the talk. Let's take 3 minutes break and we'll start the next seminar.